All right, so we're diving deep into feature engineering for machine learning today. And wow, you weren't kidding about wanting the full picture. You've sent over a Kaggle Grandmaster interview, Fei Li's Stanford page, Reddit threads, even some Wikipedia, and that feature engineering book.
It's a lot, yeah, but that just shows you how important feature engineering is. It's like the core of almost every machine learning project out there.
Okay, so before we get lost in the weeds, for anyone just tuning in, think of feature engineering like
Mm.
prepping your data, right? Like you wouldn't just chuck random ingredients into a pot and expect a gourmet meal.
Exactly. You can't just feed raw data to a model and hope for amazing results. You got to transform it. First, you take that raw data, like text, numbers, images, whatever you got,
Hmm.
and turn it into something the algorithm can actually use. And the quality of that data meal, those features, that's what determines how well your model's going to perform.
Right, it's garbage in, garbage out. Now, one of the things you sent over was this YouTube interview with Dmitry Larko, a Kaggle Grandmaster. I gotta admit, that whole Kaggle scene, it's pretty competitive, right?
Right. Yeah, Kaggle's like the ultimate testing ground. It's where all the data scientists and machine learning folks go to, flex their skills. They have these competitions. People from all over try to build the best models for some really tough problems, becoming a grandmaster. That's not easy. You need serious talent and dedication.
So this Larko guy, he had some interesting things to say about his approach. He's all about thinking about the problem constantly, like obsessing over it.
Mhm.
And he talks about using the Kaggle community, learning from others, trying tons of things quickly to see what sticks.
And that's actually super relevant to feature engineering. You're doing the same thing, right? Experimenting with different ways to represent the data, seeing what makes your model better, and just constantly refining,
Like
refining.
he even said he only sleeps 5 hours a night, so he has more time for Kaggle. I admire the dedication, but I think I need my beauty sleep. Anyway, let's get specific here. Larko talked about categorical features, gave the example of visa in the transcript. What exactly are those?
Okay, so categorical features, they basically represent categories or groups in your data. Think of things like colors, red, blue, green, or types of cars, or in this case, credit card types, Visa, MasterCard, and so on. The tricky part is most models like numbers, so you got to figure out a way to represent these categories numerically.
I can see where this is going. You can't just randomly assign numbers to them, right? That'd mess everything up.
You got it. Let's say you give Visa a 1, MasterCard a 2, American Express a 3. The model might think, oh, MasterCard's bigger than Visa, which obviously makes no sense. So smarter techniques are needed, and Larko mentioned a few.
Lay 'em on us.
One that's super popular is one-hot encoding. Basically, you create a separate feature for each credit card type. So Visa would become like 100, MasterCard would be 010, and so on. That way, there's no weird ranking implied between them.
Clever. But I'm sensing a but coming.
There is. With one-hot encoding, your data set can get really sparse, especially if you have a ton of categories. You end up with a bunch of zeros, which can be a pain for memory and computation. It's a trade-off.
Makes sense. What about the other tricks Larko had up his sleeve?
Another option is frequency encoding. So you replace each category with how many times it shows up in your data. If Visa appears 500 times, MasterCard 300, you encode them as 500 and 300.
Isn't that kind of like the ranking problem again?
Not exactly. Here, it's not about ranking, but more about showing how common each category is. But you do have a problem if two categories have the same frequency.
Ah, the model wouldn't know the difference.
Right. Something to watch out for. Now, target encoding, that's the third one Larko mentioned, and it's a bit more complex.
Hit me with it. I'm feeling like a Kaggle competitor already.
All right, so with target encoding, you replace each category with the average value of your target variable, but just for that category. For example, you're predicting ad clicks, right? If historically people with Visa click on ads 60% of the time, you encode Visa as 0.6.
That seems like a pretty strong signal for the model.
Yeah.
But wait, there's got to be a downside, right?
You're good at this. The danger is data leakage. That's when info from your target variable, the thing you're trying to predict, leaks into your features during training. Like giving your students the test answers beforehand. They might ace it, but haven't really learned anything.
Sneaky. So how do you stop that leakage?
There are techniques like smoothing. It kind of mixes the target average with the overall average, which helps prevent the model from relying too much on the training data and then failing on new stuff.
So with all these encoding options, how do you pick the right one?
Sadly, there's no magic formula. It all depends on your specific data, what you're trying to solve, how much data you have, even your computing power. Sometimes you just got to experiment and see what works best.
It's like the art and science of data cooking. Speaking of which, let's shift gears to a different ingredient, Text data.
Text data, the language of the internet. It's everywhere these days.
And we see it popping up everywhere, from Fei-Fei work to those Reddit threads about LLMs. That feature engineering book also talks about turning words into something a machine can understand. But how do you get a machine to grasp the meaning of words? They can't just read and interpret like we do.
That's where feature engineering comes in. It's all about turning those words into numbers, something the algorithm can work with. And a simple but powerful way to do that is bag of words.
Bag of words. What's in the bag?
Imagine you have a document, let's say a news article. You take all the words and chuck them into a bag. You don't care about the order or the grammar, just how many times each word shows up.
So, like a word count for the document.
Yep. You end up with this vector. Each element represents a word, and the value has how often it appears.
If election appears 5 times, its value is 5. Got it.
Exactly. It's simple, but surprisingly effective for some tasks.
I can see how that captures the general idea, but doesn't it totally ignore word order? Context matters in language.
You're right. Bag of words does lose some nuance by ditching word order and grammar, but it's still a great tool for getting a feel for the topics in a document.
Like getting the gist, even if you miss some details.
Mm-hmm.
So how do we capture more context, more meaning?
That's where n-grams come in. Instead of single words, you count sequences. Bigrams look at pairs like election results or artificial intelligence, trigrams, 3 words, and so on.
That's a smart way to keep some of those relationships between words and preserve more meaning. So how do you decide how many words to include?
Picking the right n depends on what you're doing and how much context you need. It's another one of those feature engineering choices where experimentation is key.
Noticing a theme here. Any other text-based tricks we should know?
Oh, tons. But one worth mentioning is TF-IDF, which stands for Term Frequency Inverse Document Frequency.
Okay, gotta admit that one sounds a bit intimidating.
Don't worry, it's not that bad. Imagine you're trying to figure out which words are most important in a document. Words that appear a lot in that document but rarely in others are probably pretty important, right?
Yeah, like the unique ingredients that make a dish special.
Exactly. TF-IDF gives higher weight to those words that show up a lot in one document, but not so much in others, because they're probably more informative about that specific document. It's used everywhere, from search engines to classifying documents.
I like that way of thinking about it. So, bag of words, n-grams, TF-IDF, we're building quite the text wrangling toolkit.
We are, but these are just a few examples. The world of text-based feature engineering is vast, and it's constantly growing.
It's mind-blowing. Now, gotta ask, how does this all apply to images? Fei-Fei Li's work in computer vision shows how important that's becoming. But images seem so complex. How do you even start turning an image into something a machine can understand?
That takes us to image feature engineering. We're trying to get those algorithms to see the world like we do, extracting meaningful info from images.
Images are so different from text, though. What makes them so tricky for machines?
Think about it. To a computer, an image is just pixels, a bunch of numbers for colors. It doesn't know if it's looking at a cat, a car, or a mountain.
Like seeing the world through a very numerical lens.
Yeah. The goal is to extract features that capture the essence. Edges, shapes, textures, patterns, so the machine can start making sense of what it sees.
Okay, starting to get it. What are some of the techniques for extracting those features?
2 classics that have been super influential are SIFT, Scale Invariant Feature Transform, and HOG, Histogram of Oriented Gradients.
Mouthful acronyms. Break them down for me.
All right, SIFT is like finding landmarks. It focuses on key points like corners or interesting patches and their orientation. It doesn't matter if the image is scaled, rotated, or even if the lighting's different.
So recognizing a building from different angles and distances, even in different light.
You got it. SIFT finds those defining features that make an object recognizable, even if it looks a bit different. HOG, on the other hand, is all about gradients, essentially edges and contours. It's like mapping the image's most prominent lines and curves.
So SIFT is for key points, HOG is for edges. Both sound super useful for object detection, image recognition, stuff like that.
Yeah, they are. These techniques have led to so many advancements in computer vision, from facial recognition to analyzing medical images.
Amazing. Now, before we get too caught up in the image world, I want to go back to that research paper recommender system in the feature engineering book.
Oh, yeah, that's a great example of combining multiple techniques to solve a real problem.
It uses bag of words for the abstracts, which we talked about, but it also has some new ideas. Walk me through how you'd build something like that.
Sure, first you got to figure out how to represent the research papers themselves start with basic stuff: year of publication, authors, fields of study.
Like creating a profile for each paper.
Exactly. And to represent the content, use bag of words or TF-IDF on the abstracts, just like we discussed.
Okay, that's the foundation. But how do you actually recommend stuff? It's like a huge database of papers. How does the model know what to suggest?
That's where collaborative filtering comes in. It uses what similar users like to make recommendations. Say you love machine learning papers. It finds others who also like that and sees what else they've read. It's like getting suggestions from a friend with similar taste.
Ah, so that's how those people who bought this also bought things work. It's finding patterns.
Exactly. But there's a catch. Imagine tons of papers, each with tons of features. That's a lot for the model to handle.
Yeah, it could get bogged down.
That's where feature reduction and selection come in methods like PCA or feature hashing. Simplify the data without losing too much info, like streamlining the recipe.
Starting to see the big picture here.
Good. But remember, this is just one example. There's a whole universe of feature engineering out there, and it's constantly evolving.
Back for more feature engineering fun. We covered so much last time, but I'm ready to dive deeper.
Me too. There's always something new to learn in this field.
So, flipping through that feature engineering book, I came across bin counting. Honestly, not the most exciting thing.
I know, right? Sounds kind of boring. But don't let that fool you. Bin counting is super useful, especially for huge data sets.
Okay, you've got my attention. What is this bin counting magic, and why is it so powerful?
Think of it like this. You've got a massive spreadsheet, tons of data. Bin counting is like sorting that data into buckets based on their values. Then you count how many data points end up in each bucket. It's all about simplifying things when you're drowning in data.
So instead of staring at every single data point, you group them into bins to get a better overview.
Exactly. Like organizing your clothes. Instead of a giant pile, you've got shirts, pants, socks. Makes it way easier to find what you need.
Makes sense.
Yeah.
But how does this connect to feature engineering and machine learning?
Imagine you're predicting ad clicks. You've got data on when people clicked in the past. Instead of looking at each click, you could create bins for different times of day: morning, afternoon, evening.
And then count how many clicks each person had in each time bin. And that becomes a feature.
You got it. But here's where it gets really cool. Bin counting can also work for categorical features, even if there are tons of unique values.
Wait, what? I thought it was for numbers, like time.
It can be used for both. The book uses user clicks and ad domains as an example. Ad domains are basically the websites showing the ads.
Right, so you could have thousands of different ad domains.
Exactly.
Yeah.
And creating a feature for each one would be a nightmare. Your data set would be super sparse, your model would be slow and clunky. Bin counting offers a way around that.
Okay, I'm hooked. How does it work?
You create bins based on how often user domain combos lead to clicks. Bins with high click rates might mean certain users are super likely to click ads from certain domains, and those bin counts become features for your model.
So instead of user clicked on domain X, you have user clicked in bin Y, where bin Y represents a bunch of domains with similar click patterns.
That's the idea. It's a really smart way to compress information and make your model more efficient.
This is pretty powerful stuff. It's all about finding clever ways to represent the data without losing the important stuff.
Exactly. It goes back to that Kaggle grandmaster mindset. Feature engineering is all about creative problem solving, finding those elegant solutions.
This bin counting thing is definitely clicking for me now, pun intended.
Glad to hear it. But like any tool, bin counting has its quirks. Got to be careful about how you choose the bin boundaries.
Right, too big, you oversimplify things. Too small, no benefit from the grouping.
You nailed it. It's about finding that sweet spot. Not too big, not too small, just right. There are different strategies for choosing those boundaries, and the best one depends on your data and what you're trying to find out.
So bin counting helps simplify data and create useful features, but you got to use it wisely, pay attention to the details.
Absolutely. That's true for all feature engineering. It's not just blindly using algorithms. It's about understanding the nuances, making smart choices, and getting your hands dirty with experimentation.
Speaking of experimentation, let's go back to image feature engineering for a sec.
Yeah.
We talked about SIFT and HOG, those classic techniques, but those came before deep learning took over.
You're right. Deep learning has changed the game for computer vision and image feature engineering.
That's what I'm curious about. How has deep learning changed how we approach image feature engineering?
One of the biggest changes is automation. Instead of us manually designing features like SIFT and HOG, deep neural networks can learn them directly from the data.
So the machine figures out what's important in the image, without us telling it what to look for.
Exactly. It's revolutionary. And this ability to learn features has led to huge improvements in how well computer vision systems work.
That makes sense. But honestly, I'm still kind of lost on how these deep neural networks work. Can you give me a peek inside?
Imagine a neural network as layers, each one doing something different to the data. For images, the first layers might find simple features like edges and corners, similar to HOG.
So the network builds up its understanding from scratch, starting with those basics.
Exactly. And as you go deeper, the layers start combining those basic features into more complex ones. They might detect shapes, textures, or even objects. It's like building with blocks.
So the deeper you go, the more abstract and complex the features become.
Exactly. It's like starting with brushstrokes and ending up with a whole painting. The network learns which features are best for making good predictions through backpropagation.
Backpropagation. Sounds kind of sci-fi. Can you explain it in simple terms?
Think of it like this. You give the network a bunch of images, and it tries to guess what's in them. Then you compare its guesses to the right answers, telling it what it got right and wrong. Based on that feedback, it tweaks itself to do better.
Like giving it a pat on the back for good guesses and nudge when it's off.
Exactly. It's trial and error, but it gets better over time.
That's incredible. So with deep learning, the machine is not only predicting, but also learning how to extract the best features to make those predictions even better.
You got it. And that's why deep learning has been such a game changer. It lets us move beyond a lot of the manual feature engineering we used to do, especially for images.
That's a huge leap forward. So is deep learning making feature engineering obsolete then?
Not at all. I think it's actually creating more opportunities for creative feature engineering.
Really? How so?
Well, deep learning models can be data-hungry beasts. They need tons of data to train well. Feature engineering can help by making the data more compact, giving the model a concentrated dose of information.
So it's like pre-digesting the information, making learning more efficient.
Exactly. Another area where feature engineering is still crucial is interpretability. Deep learning models can be black boxes. We don't always know why they make certain predictions.
Right. That's one of the big worries about deep learning. It can seem like magic.
It can, but feature engineering can help us build more transparent, understandable models. By carefully choosing and creating features, we can see how the model is thinking.
That's crucial in fields like healthcare or finance, where you need to explain those decisions.
Absolutely. Feature engineering isn't just about performance, it's about building trust and making sure our models align with our values.
Okay, it's all coming together. But with all these different techniques, from simple to complex, how do you choose the right ones? Any secret formula?
I wish it were that simple. Feature engineering is an art and a science. No one-size-fits-all answers. The best techniques depend on a bunch of factors.
Like what? Give me some hints.
First, what kind of data are you working with? Text, images, numbers, or a mix? That'll guide your initial choices.
Makes sense. Different data, different tools.
Right. Then think about your goal. What are you trying to do? Classify images, predict customer churn, recommend products. Each task might need different features.
So the goal dictates the ingredients. What else?
The size of your dataset matters a lot. Small dataset. Be careful about overfitting. Computational resources are always a factor too. Some techniques, like deep learning, need serious computing power.
Right. Got to have the right tools for the job. Can't bake a cake at a toaster oven.
Exactly. And don't forget about domain expertise. If you're working in a specific field, understanding that field can help you find features that aren't obvious from the data alone.
So if you're predicting stock prices, it helps to know something about finance.
Definitely. Domain expertise can be a huge advantage.
Okay, so no easy answers, but lots to consider when choosing techniques. Sounds like experience and intuition are key.
They are. Feature engineering is a field where creativity and experimentation are super important. Don't be afraid to try things out and see what works for you.
This is all fascinating. But why is feature engineering so fundamental to machine learning? What makes it so important?
At its core, feature engineering bridges the gap between raw data and the models we use to understand that data.
Like translating the language of data into something machine learning models can grasp.
Exactly. Our models are only as good as the data we feed them. Bad features, bad results, even with a fancy model.
Like giving a chef rotten ingredients. No masterpiece coming out of that.
You got it. Feature engineering is about finding the most meaningful signals in the data, giving your models the best chance to succeed.
So it's not just about formatting the data, but also highlighting the parts that matter most.
Absolutely. It's about curating the data, presenting it in a way that makes it easy for models to learn and make accurate predictions.
This really shows how crucial feature engineering is. It's the foundation for building successful models.
Couldn't agree more. And as machine learning keeps evolving, feature engineering will only become more important.
It's a field with a bright future, that's for sure.
Absolutely. And it's full of exciting challenges and opportunities for innovation.
Welcome back for the final stretch of our feature engineering deep dive.
Yeah.
It's been quite a journey. We've covered so much ground. And I feel like I've got a much better grasp on what makes machine learning tick.
Yeah, it's been a wild ride. From the basics to some pretty advanced stuff, we've seen how feature engineering is like the unsung hero of any machine learning project that actually works.
It's crazy how much creativity goes into it.
Hmm.
It's not just following a recipe. You're always trying new things, looking for those hidden patterns in the data.
Absolutely. It's a mix of art and science. You need the technical know-how, but you also got to have that intuition, that ability to see the data in new ways and come up with those clever solutions.
One thing that really jumped out at me from those Reddit threads was just how fast feature engineering is changing. There are always new techniques popping up, new challenges to tackle.
It's a field that never stands still, that's for sure. And the rise of deep learning has been a huge part of that. We talked about how it's automated a lot of the feature engineering process for some tasks, like images, but that doesn't mean traditional feature engineering is going extinct. Not at all.
I'm curious about that. If deep learning can automate so much, what's the role of those older techniques? Are they still relevant?
Definitely. Deep learning has its quirks. For one, those models can be real data hogs. They need tons of data to train properly. Feature engineering can help by making the data more compact, giving the model a more concentrated dose of info, if you will.
It's like condensing a giant textbook into a cheat sheet, highlighting the key points so you don't have to read every single page.
Perfect analogy. And there's another area where those classic techniques shine: interpretability.
Right. Deep learning models can be these mysterious black boxes. They give you amazing results, but it's not always obvious how they got there. And that can be a problem in fields like healthcare or finance, where you need to be able to explain those decisions.
Exactly. Feature engineering can help us build models that are more transparent, easier to understand. If we know which features are driving the decisions, we can get a better grasp of the model's reasoning and make sure it aligns with our values and ethical considerations.
It makes perfect sense. It's not just about performance, it's about trust and making sure those models are doing what we want them to do.
And speaking of trust, that reminds me of something else we saw in the Wikipedia article: the potential for bias in machine learning models.
That's a critical point. Machine learning models are trained on data, right? And if that data reflects existing biases in society, the model can actually perpetuate and even amplify those biases. That's a sobering thought. It really highlights the responsibility we have as data scientists and machine learning engineers to be aware of potential biases in our data and in our models.
Couldn't agree more. And feature engineering has a huge role to play in mitigating bias. We need to be super careful about which features we choose and how we engineer them, making sure we're not accidentally encoding or reinforcing harmful stereotypes. It's not just about technical skills, it's about being ethically aware and socially responsible.
It's about building models that are not only accurate, but also fair and just. Using this technology for good, not for causing harm.
Absolutely. We need to be mindful of the impact of our work and strive to build models that benefit everyone.
This whole deep dive has been an eye-opening experience. We've gone from the basics to the bleeding edge, explored a ton of different techniques, and even talked about the bigger picture of what this field means for the world.
It's been a blast. I've loved exploring all this with you.
As we wrap things up, I want to leave our listeners with a question to ponder, and it's one I'm asking myself too. If you could build a machine learning model to solve a problem in your own life, what kind of features would you create and why?
That's a great one. It really makes you think about how we can apply these ideas to our own lives, to use this powerful technology to make a real difference in the world around us.
Well said. I think that's a perfect note to end our deep dive into the fascinating world of feature engineering. It's been a wild ride, and I hope everyone listening has enjoyed it as much as we have.
To everyone tuning in, keep exploring, keep learning, keep pushing the limits of what's possible with machine learning.
And remember, the data is out there, just waiting to be transformed into insights that can change the world.